This is lesson 3.3, slopes of lines. All right, students, we're just working on the 2 warm-up problems. So I'm going to go over number 1 right now. In the diagram below, if the measure of angle 1 is 79 degrees, find the measure of each numbered angle. Okay, so what I notice right away is I see these 2 arrows on these lines, meaning they are what? Parallel, yep. Okay, so 2 parallel lines. Here's my transversal. So lots of relationships going on here. We can figure out all the other angles if we only know one of them. All right, let's start with 2. What's the relationship between angle 1 and angle 2? They're supplementary, or they're a linear pair, and their angle measures add up to what? 180. So 180 minus 79 is 101. Measure of angle 2, 101 by supplement. What's the relationship between angle 2 and angle 3? They're vertical angles, which means they're congruent. So that's also going to be 101. Or you could say it's supplement to angle 1. You could say that too. So similarly then for angle 4, you could say it's vertical to angle 1 or it's supplement to angle 2. That one's also going to be 79 degrees. Okay, cool. Angle 5. Now, based on what's given to us, what's the relationship between 1 and 5? They're corresponding, which means they are what? Congruent, the same measure. So angle 5 is 79. Another way we could have figured this out, because we know angle 3 and 5 are consecutive interior, meaning they lie on the same side of the transversal, meaning they add up to 180. Okay? Then from there, a couple ways you could do this. 6, you could say alternate interior to angle 3, so it's congruent, or it's supplementary to angle 5. That one's 101. Okay, angle 7's vertical to that one, 101. 8. Alternate exterior from angle 1, alternate exterior are congruent, or you could say it's vertical from angle 5. Lots of different relationships we could describe there. Okay. If you haven't tried number 2 yet, I'm going to give you 30 seconds to try it. Oh, did you find your test? Oh, perfect. Never mind. Let's do it then. Okay. So I define x and y. So looking at my 2 angles that contain the x, because I'm probably going to have some relationship there so I can solve for it. I see my 2 parallel lines are these 2 horizontal looking lines, this one and this one. Meaning my transversal is that one right down the middle. So what's the relationship between these 2 angles? Say it louder, Lillian. I think you're right. Oh. Oh, that was Gwen. What did you say? Alternate, opposite sides of transversal, exterior, right? They're both exterior. They're lying outside the parallel lines. You guys know the relationship between alternate exterior angles? They're congruent. Yep, alternate exterior angles are congruent. So we'd say this angle is the same as this angle. It doesn't ask us to do this, but on the quiz you're going to have to. Don't let me forget to give you the quiz review too. By alternate exterior angles. All right, let's quickly solve this. We got x to be 16. Another way you could say this, guys, that they're the same. This angle and this angle are corresponding. And this angle and this angle are vertical. So you could say corresponding and vertical. Meaning they'd be the same. Does that make sense? Okay. Now that we know what this angle is, because we know what x is, what's the relationship between these 2? Supplementary. So they're going to add up to what? You guys awake? You awake?
Ma'am.
Okay, good. 10 times x is 16 minus 27. That's usually the easiest way to see this one. Plus 2y plus 9 is that, hey, these are supplementary. by supplement. You could also say corresponding and supplement. And use this one if you wanted to. Okay? Alrighty, folks. Quickly solve this. I got y to be 19. Okay. That's your review over 3.2. So 3.3, we're talking about slope. Man, is that a throwback to Algebra 1? Good times on the ranch. I love slope.
Why?
It's just, there's so many things you can do with it. Okay. And if you ever get to take calculus in your career as a student, we talk about slope for like the whole first semester. But not just like slope, like of a line, like slopes of lots of things, like curves. And you're like, wait, how can a curve have a slope? It's not straight. It can have it at a point. Anyways, it's important, okay? So let's see what we remember from slope. So when we're talking about just lines, though, the slope tells us two things about our line. One of the things it tells us is which direction it's going. One of our 4 directions. The second thing it tells us is how steep the line is. Okay? So our slope is a number. It's a ratio. You can write this down. And to give us that steepness, we write it as a ratio of the vertical rise to the horizontal run. And the two things slope tells us about our line is the direction, and that's by the sign, and the steepness, and that's by the ratio, by the number. Lines that have really big slopes, really big numbers, are really steep. Lines that have ratios that are close to 0, such as like 1/2 or even like 1/8, those are like flatter lines. Okay, they're less steep. So it tells us the steepness and it tells us the direction. Okay, so to figure out like the vertical rise, I like this little picture over here. This right here shows me the vertical rise of this line. So how I get from this distance, or how I get from y1 to y2, is we figure out like what the difference of those coordinates are. That would tell me, you know, if I ended here and started here, the difference of those would tell me how much my line rose vertically. My horizontal run, okay, and think of like on a coordinate plane, your axes here. Well, if I started here at x1 and finished here at x2, the difference between those endpoints would tell me my horizontal run. Okay, so there's a couple of different ways we can describe slope. First of all, do you guys remember what variable we use for slope? What letter? E?
B.
B. No. M. M. B is y-intercept. I think that's what you're thinking of. Do you guys know why we use M?
No.
This is a fun fact.
The person that created slope started from there.
No, but good guess. But I know the person who created slope was French, because it comes from a French verb, monter. That's my French accent. This means to climb in French. It means to climb. Isn't that a cool fact? Okay. You've probably heard this before, that your slope is your rise over run. And that's the ratio part of it, guys. It's your ratio of the vertical rise to the horizontal run. Okay? You probably heard this too. Your change in y, that's this, your change in y, that would give you your rise over your change in x. That symbol there is called delta. It means change. You haven't seen that before. It's not too important now. Or this, you probably remember from Algebra 1, our little like slope formula to calculate slope And we have it written right here for us because I know my change in y would be the difference in my y coordinates, y2 minus y1, over my change in x, x2 minus x1. Remember that? Is that ingrained in your brain?
It's ingrained in like 1/4 of my brain. Like I forgot about it, but you just kind of opened up like, oh wow, I remember.
Oh, good.
No, these are bad memories.
Oh. Time to recreate on this good memory. Okay. So here's our 4 possible directions that our line can be going. So obviously, you know, this is going to calculate like our ratio, how steep the line is. And I have 4 possible directions that the line can be going. Here, if I read this like a book, left to right, this line is rising. What does that mean in relation to our slope? Anyone remember? It's a positive number, exactly. It's a positive ratio. At the end of class today, we'll watch a little short film, this length, about slope. It's fun. And that'll kind of help you. But read it like a book, left to right. If it's going up, positive slope. If it's falling from left to right, negative ratio. Yep, negative slope. All right, and then we kind of have those 2 weird case scenarios. If we have like a horizontal line and if we have a vertical line. Do you guys remember what horizontal lines have slopes of?
0.
0. Yep. What about vertical lines? Undefined. Nice, Tyson. Undefined. Here's how I remember it. If I trace a horizontal line, pretty easy to draw a Z for 0, right?
Yeah.
If I trace a vertical line, pretty easy to draw U for undefined. Maybe that'll help you.
That's not gonna help.
Okay, maybe the short film will at the
I'm
end of
just
class.
gonna remember it.
Okay. All right, so most of the class we're just gonna practice finding slope, and it's gonna be fun. You're gonna like it. Let's start with a graph, and let's start easy where they actually like plot 2 points for us on our line. All right, now I can figure out the coordinates or the ordered pair and use my slope formula, but if I'm given a graph, I just figure out what my rise and my run are. Okay. Now before I even do any calculating here, what direction is this line going? Down, so I'm going to have a negative slope here. So before I even do anything, I like to do that to remind myself my slope better come out to be negative, because sometimes students forget that. Okay? So then from there, I use the 2 points that are given to me. I could use this one because I see it clearly crosses there. Could use that one. But I'm going to use the 2 that they gave me. And all I have to do is count what's my vertical rise and what's my horizontal run. So you just basically connect the 2 dots any way you want using straight lines. You could go this way too if you want. But if you count those boxes, what do you guys get for a rise? Count again. 8. Here we get 2. So our slope, our ratio, of our vertical rise to our run would be 8 over 2. Factoring in the negative because of what the direction it's going. Now we can reduce this ratio to -4. You could do -4 over 1. I know some of you are probably trained to leave slope as a fraction. That's what I train my Algebra 1 students to do. -4 over 1. -4 is just fine too. Sometimes people will just count 8 over 2. They forget about the negative. Okay. All right, this one. They didn't give me points, so you got to find points where the lines clearly cross. You could use this one, this one, this one, this one. Doesn't matter. Let's say I'm using these 2. So I'm going to connect them. All right, what direction is this going? Positive. Okay, great. Don't need to add a negative. My rise. My run. 2. Slope is 1 over 2. And, folks, we never want to write our slope as a decimal unless we're doing word problems. But leave that as 1 over 2. If you can reduce it, reduce it. Obviously, 1 over 2 can't be reduced. If you would have done this point to this point, you'd have gotten 2 over 4. Reduce it to 1/2. Okay, remember that? Yeah. Great. All right, what if I'm not given a graph, I'm just given two ordered pairs? This is when we're going to have to use our good old trusty slope formula. And I'm going to rewrite it here because you need to memorize this for the rest of your life. If you don't want to memorize it, you better get it tattooed. That's the only way I'd let you use it, if you get a real tattoo of the slope formula on a test. y2 minus y1 over x2 minus x1.
What if I get one of those like non-permanent
No.
ones that like wash
No.
out in a week? Oh.
Has to be permanent. And none of you are old enough to get tattoos, so. Sometimes I forget. Okay.
Actually,
We're recording,
Illinois,
guys.
yeah.
We're recording.
In Illinois, you can be 16 with pair permission.
Okay. So what and again, I know I obviously wasn't your Algebra 1 teacher, but when I taught Algebra 1, I was just told my students, treat this, just like distance formula 2 when I taught this, treat this as x1, y1, treat this as x2, y2, use the little sub coordinates as like, hey, this is my first point, hey, this is my second point, and then you won't make any mistakes. So we got y2, which is 6, minus y1, which is 11, all over x2, which is 5, minus x1, which is negative 2. Okay. Now you just have to make sure the ones that are like stacked on top of each other, those should be the ordered pairs. So 5, 6, negative 2, 11. Okay, as long as you have the ordered pairs stacked on top of each other, you're good. All right, folks, we have 6 minus 11 is negative 5. Over 5 minus negative 2 is 7. Can that be reduced? No. Show me with your arms, what direction will this line be going? This way. Yeah. Negative, right? Negative.
I was doing it so she's
Keep switching. Come on. Okay. Here's where sometimes slope can get a little bit confusing when we put it in context of a problem. But your slope is just a rate of change. Okay? That's another way to kind of like describe slope, and that's what we talk a lot about like in calculus, is our slope is just like a rate of change. Have you ever seen me put ROC? That just is short for rate of change. And it's really just our slope. The best way I like to describe it is you basically have, in context of a word problem, you have the change in one quantity over the change in another quantity and usually the change in another quantity, the one on bottom, is usually some sort of time unit. And that can kind of help you work through some of these. It's usually time.
Time is always x.
Usually.
No,
Time is our independent variable.
Time is whenever time is anywhere on a graph, it's always x. That's
Yeah.
why I
Yeah. And it's our independent variable. Yep. Okay. So let's try just one example of a word problem here, and then we'll get to our last postulate. So in the year 2000, pre-year time, the annual sales for one manufacturer of camping equipment was $48.9 million. Nice. In 2005, the annual sales were $85.9 million. Okay, are our sales going up or down? Up. That's great news if we are this manufacturing company. If sales increase at the same rate, what will the total sales be in the year 2015? Okay. So I see I have a change in two quantities. I have a change in the amount of money, and I have a change in time. My change in my sales, let's write this as a rate of change, would be the difference of what the sales were in 2005 and what they were in 2000, in the year 2000. Now, Also, like a hint, you want to look for like matching units. So I see dollar, millions. Okay, so that's usually like a hint at what kind of quantities match here. So we're going to do 85.9 minus 48.9. And that lets us figure out how much the sales went up over those 5 years, right? Which that's 37. That's not like how much total. $37 million. That's the same as my salary. How ironic. Just kidding. That was supposed to be funny. Okay. You guys don't get it. All right, now my change in time is we have obviously 5 years here. But in 2005, and remember these should always match, 2005 we had that 85.9 million. And in 2000 we had that 48.9 million. So obviously my change in time was 5 years. All right. Now this is the weird case when we don't want to keep our rate of change as a fraction. So if we do 37 divided by 5, we get 7.4. Okay, let's think about units here for a second. So in my numerator, these were in $1 million. So the sales increased $37 million over 5 years. So what's this number? It is a slope. But what is it in
miles per year?
Yep. Million per year. Yep. How much it changed each year? 7.4 million. You can say per year, and here's what you say each year. That's how much it increased in just 1 year. Now we could check this math by starting in 2000, add 7.4 million to figure out what it is in 2001, add 7.4 million to figure out what it is in 2002, et cetera, et cetera, et cetera. Or we could just times that number by 5. We'll get 37. That's how much it increased. And that's why 48.9 plus the 37 will give me here. Okay, kind of follow that thinking. And that's going to help us in the next step. So what will our total sales be in 2015? Well, if it's growing 7.5 or 7.4 million each year, let's say we're starting in year 2000. Let's just do that. In year 2000, how much do I already have from this equipment? How much were my sales already at in 2000? Okay, so that's how much they were in 2000. And then they increased 7.4 over the next 15 years each year. So times that by 15. Instead of adding 7.4 15 times from the year 2000. Could you have done 2005 and then done 7.4 times 10? Yeah, you could have done that too over the next 10 years. Yes.
Did you just add 37 over 5 twice?
What do you mean twice?
Like the fraction.
I don't get what you're saying. 37 over 5, add it twice to what?
To itself. Be 10. So it's 10 years. 85.
Technically, you could
I
have just
don't
taken
even know.
what she's saying
I see what you mean. I just don't know where.
I don't know.
What I was saying is you could also do, you could also figure out what it, in 2005 we're already here. And then you could say it's growing 7.4 over the next 10 years. That'd get you the same number. That's what I was saying. 37 fifths. Oh, so you could figure out how much it was in 10 years? Yeah. That would work. Yeah, okay. Either way, we get that $159.9 million. That's a lot of moolah. All right, the last thing I have to talk about. Let's see if you remember this from Algebra 1. So this is how it kind of connects to what we've been talking about. We've been talking about parallel lines and even perpendicular lines a little bit, but mostly parallel lines. So now connecting slope with parallel lines. Do you guys remember the relationship between parallel lines and their slopes?
No, the same.
They're the same, which makes sense because the only way that two lines could never intersect would be if they're going in the same direction at the same steepness, which is our slope, at the same rate, right? Look, here's an example. These are marked parallel. What are their slopes both? 4. Parallel lines. This is a postulate, something we just accept as truth, even though there's no proof to it. Parallel lines have the same slope. Okay, let's see if you remember this one. So now I threw in a perpendicular line here, line P. There's kind of like two criteria with perpendicular slopes. Anyone remember it? Now there's a little hint here with some numbers. Tyson? You can guess. It's okay to guess and be wrong. Yes, they have to form a 90-degree angles. You're right. But what about their slopes? What's their connection with their slopes? Alejandro?
It has to be technically the same slope, but in the other direction.
Okay, opposites. Yep, that's one. So in the other direction, meaning one's positive, one's negative. Yep, opposite. There's something else. Because if they were just opposites, this slope would be 4 and this slope would be negative 4.
Switching the x1. I don't know how to explain that.
Reciprocal. Yep, reciprocal. Nice. Opposite. Reciprocal. Reciprocal in math, folks, means you flip the numerator and denominators. So 4 over 1 becomes 1 over 4. Okay. Perpendicular lines have opposite reciprocal slopes. Okay, we just have 3 more example problems to do. Determine whether FG and HJ are parallel, perpendicular, or neither for, and then they give us all the order pairs for FG, H, and J. Graph each line to verify your answer. Okay, so we're going to do this using slopes. So for FG, let's start with finding that slope. We're going to have to use our slope formula. We could graph it and do rise over run, but they just want us to use the graph to verify. All right, so we have y1, which is negative 1, minus y2, which is negative 3, all over x1, which is negative 2, minus x1, which is 1. I might have said that backwards. x2 minus x1. I can't remember what I said now. All right, either way, I wrote it correctly. Up here, negative 1 minus negative 3 would turn into plus 3. We get 2 over negative 2 minus 1 is negative 3. That fraction can't be reduced, so just leave it. So there's FG. Now HJ, which are these, contains these 2 points. Let's calculate that slope. So we got x1 and y1, x2 and y2, 3 minus 0 over 6 minus 5. All right, so you get 3 over 1, which you can leave it like that, or that's just 3. All right, so first of all, are they parallel? Are these the same ratio? No. So they're not parallel. In order for them to be perpendicular, they have to be opposite, which they are. One's positive, one's negative. But are they reciprocals of each other? No, and it has to be both. Okay, so they're not perpendicular. Therefore, these are neither. Okay, let's go ahead and graph these to verify. So we're just going to plot these points 1, negative 3. That's point F. Negative 2, negative 1. There's G. You can draw a line. If you wanted to be more accurate, if you didn't have a straight edge, you could graph your slope of 2 over negative 3. Your rise over your run. HJ, we have 5, 0. That's an x-intercept at 5. 6, 3. All right, so after we graph these, we can definitely see they're not parallel. Oh, I just missed really badly, but it's okay. They're definitely not parallel. They look like they could possibly be perpendicular. We know they're not because we calculated the slope, so those don't form a right angle. And if you use a straight edge, it's hard for me to graph up here, but if you use a straight edge, they should not look perpendicular. But you also can't just say 2 lines are perpendicular because it looks like they cross at a right angle. You can't say that. You have to either prove it using slopes or you have to use like pi theta to prove that it is a right angle. Okay. You guys try this one. Determine whether A, B, and C, D are parallel, perpendicular, or neither. And there's all your ordered pairs for A, B, C, and D. Give you a couple minutes. All right. For line AB, I got 6 over 6, which reduces to 1. You can write it as 1 over 1 if you want. Here I got negative 3 over 3, which reduces to negative 1. All right. Are these the same slopes? No, so they're not parallel. Are they opposites? Are they reciprocals? Yes. Meaning they are perpendicular. Okay, any questions? All right, we just have one more. This one's kind of a fun problem to end on. Graph the line that contains point Q, which is located at 5, 1, and is parallel to MN with M located at negative 2, 4, and N located at 2, 1. All right, there's a couple ways you could tackle this. You can use your slope formula to figure out what the slope is here, but I personally, since I have to graph this anyways, I'm going to graph negative 2, 4. I'm going to graph MN. Oh, no. Let me try that again. Because I'd rather count my rise over my run, but that's up to you. If you want to use the slope formula, you can. And then I can figure out what the slope of this line is. So I have a rise of 3, run of 4, and it's going down. So this slope is negative 3 over 4. Okay, you could have also used slope formula to find that. Since Q, the line that contains Q, is parallel to this, what does that mean? It's going to have the same slope, exactly. It's also going to have a slope of negative 3 over 4. Okay, so point Q, we're here at 5, 1. And this kind of helps you give a visual. We're going to have to go rise of 3. Now, since we're going negative, I usually just go down 3, and then I always run to the right. If it's positive slope, I go up and then run to the right. However, you were taught to kind of plot slope, but should be going obviously in the same direction. Down 3 over 4. or we can go up and left. Make sure when you're graphing lines, you put arrows. And then this connects back that these are indeed parallel, and it passes through that point 5,1. Okay, the only last thing I want to show you, because slope deals with a lot of fractions, is basically how you can deal with like decimals and fractions and mixed numbers kind of in your calculator. Because some people in my last class said that they didn't know how to do this in their calculator. Okay. Now, don't get me wrong. This is not like crutching your ability to like do mental math with fractions and stuff. This is just to kind of like help you when you get some tougher fractions or when you're dealing with slope, because fractions come up a lot. Okay. So if you want to follow along on your calculator, you can. Otherwise, you can just watch my dot cam. All right. So first of all, let's say I get a decimal. Like, let's do 2/3. So let's say I have 0.6 repeating. If you want to know what that number is as a fraction, obviously we know that one's 2/3. So there's this button right here where it's like change F and it has a D. That means fraction decimal or decimal to fraction, wherever you want to go. And it's in that like light blue or that purpley color. So we have to hit the second button, and then we're going to tap the PRB, that stands for probability. We're going to tap that button, and it'll change it from a fraction to decimal. It'll put it in a fraction for you, 2/3. Another way to get fractions in your answers is to use this fraction button. So instead of typing 2/3 as a division problem, like 2 divided by 3, you can use this button, type the numerator, this button. Oh, I think I hit the decimal point. Hit the numerator, hit this button, 2/3, and it'll kind of keep it as a fraction for you. So say we want to do like 2/3 plus 7/9. Okay, something like that. And it'll give you the fraction then. If you want to know what it is as a decimal, you can hit this button. I'll change it to a decimal for you. Want it back to a fraction? Here. Now, we don't love mixed numbers, especially when we're working with slope. Guess what? There's a button for that too. That's the one right above your fraction 1. So it's that purpley one, that A, B, C to D over E. Hit that button. It'll give it to you in an improper fraction. All right, that's kind of what's laid out in that diagram there for you. Okay, I'm going to pass out the worksheet and quiz review. Let me stop the recording quick.